Well, we're moving right along in chapter 11. Now we're going to be talking about trends in the periodic table. And there's a lot of goals for this section. We want to be able to explain things like ionization energy, atomic size, different things like that, and how it relates to the periodic table. We want to be able to identify things on the periodic table like metals and nonmetals, predict metallic character, talk about alkali metals, halogens, noble gases, which we've already been talking about, kind of bring all these concepts together and go in a little bit more in depth on the periodic table than we did in our video, I believe in chapter 5 about the periodic table. So that's kind of our goals, quite a lot of them, but not really too hard this section. So the first trend that we can observe in the periodic table is atomic size. So atomic size generally increases from right to left across any row in the periodic table and from top to bottom. So basically elements, their size of their radii, if you will, increase as we go this way across the periodic table and this way across the periodic table. Okay? So the small atoms are towards the upper right corner of the table, and the largest atoms are towards the bottom left of the table. Okay, so we can see that here. So helium or neon are really small compared to cesium. Okay, and that gives you an idea that we're increasing the size. Okay. So that's the trend that we're observing with the periodic table. So where does this come from? Well, the trends in atomic size are believed to be primarily the result of two influences. The first is that the highest occupied principal energy level. As the valence electrons occupy higher and higher principal energy levels, they're generally further and further away from the nucleus. The atoms become larger. You can think about, even though we learned that it's not technically correct, the Bohr model where these the radii increases as you go higher and higher, that's still true. It might not be planets, the planetary model like we thought about, but same idea, we could say. So for example, the valence electron of lithium is a 2s electron, excuse me, whereas the valence electron of a sodium atom is a 3s electron, which is the largest atomic radius. Well, as the valence electron occupies higher and higher principal energy levels, they're generally farther away from the nucleus. So we would say sodium is the answer here, because its electron is in a 3s orbital, which again is further away from the nucleus. Okay? So the second factor is the nuclear charge. Within any period, the valence electrons are all in the same principal energy level. As the number of protons in the atom increases, the positive charge in the nucleus also increases. And so this increasing positive charge, we can think about it pulling the electrons closer to the nucleus. So the atom becomes smaller. So again, if we look here, the atomic number for sodium is 11. So there's 11 protons in the nucleus. And the atomic number of magnesium is 12. There's 12 protons in the nucleus. Which one has the larger atomic radius? Well, again, the more protons we have, generally within the same period, okay, the same row, all right? And if you look at the periodic table, magnesium and sodium are right next to each other. When you have more protons, you're going to be smaller. So sodium, okay, is going to have the largest atomic radius again, okay? Just looking at it in both examples. Okay, so let's do another example. Put the following elements in the order of increasing atomic radius. So we have phosphorus, sulfur, and arsenic. And so one of the things you could actually do is, well, first we need to locate them on the periodic table. So sulfur is element number 16, phosphorus is element number 15, arsenic is element number 33. And one thing you might like to do is actually just kind of draw out where they are in relation to each other. And I should just note before I do that, that here is a summary of the trend, okay, that it increases going this way and down. So if we do that, we have sulfur, and then next to it on the periodic table is phosphorus. And then below phosphorus is arsenic, okay? If we just basically draw our trend, shown here right on top here, it increases going this way and down, okay? So that means in order of increasing atomic radius, sulfur is going to be the smallest, right? It's most in the top right corner, followed by phosphorus, and then arsenic is going to be the biggest. Okay, so this is an increasing atomic radius. Okay, so hopefully that made sense. And there's plenty more examples in the homework. So I'm just going to erase that for now. Okay, so let's keep going. So there's another trend that we can get from the periodic table. That's ionization energy. And so what ionization energy is, it's basically the energy required to pull an electron off of an atom, okay? So here we can say this is represented in kilojoules per mole, kilojoules being a unit of energy, mole being something we're going to talk about later in the class. But basically, it's a unit of energy. So it takes a certain amount of energy to take off one electron, all right? Another amount of energy to take off another electron, and we see that here, okay? Where an electron, if you remember in our other video talking about reactants and products, is listed as a product in this reaction, right? So if we look at this more carefully, magnesium plus some input of energy gives me magnesium cation, basically magnesium with a positive charge plus a negative electron. So I lose a negative, so I got a little more positive, right? That's what happened with magnesium here. And then again, we take that magnesium plus one, give it some more energy, kick off another electron that's negative, it gets even more positive. We're going to talk a little bit more about that as we go through the class as well. But the third ionization energy for magnesium is very high, okay? And it's usually high enough to prevent the formation of magnesium plus 3, okay? Except under unusual conditions that we won't really talk about in this class. So this is some magnesium here, actually, in case you're wondering what that is. So that's ionization energy. It's the energy required to pop an electron off of the atom, off of a neutral atom. Okay, so here is showing that here. So this is for sodium. So we have a neutral sodium atom. Here's its electron configuration. If I put energy into the neutral sodium atom, I'm removing an electron. So the neutral sodium atom, all right, loses an electron, and here's its new electron configuration. And if you actually notice, just jumping ahead a little bit, it's actually the electron configuration of a noble gas, okay? But here we go. Here's the electron configurations for those. And again, we put in energy, we kick off an electron, and now it has 10 electrons and 11 protons instead of the usual 11 and 11 for a neutral atom. And here's just a plot of ionization energies versus atomic number. And we're going to see the trend from this in a second, okay? But there can be fairly high for certain elements, especially the noble gases. Notice the noble gases, it's really, really hard to remove an electron from one of those guys. So it doesn't really happen. Okay, but that's kind of besides the point of what we're going to be talking about. Okay, so the ionization energy then, the trend is basically the opposite of size. So ionization energy generally increases from left to right across any row of the periodic table and from top to bottom in any column. The atoms with the highest ionization energy are towards the upper right corner, and those with the lowest ionization energy are towards the bottom left corner. So basically, the elements that are hardest to remove an electron are in the top right. They have the highest ionization energy. And the ones that are easiest to remove an electron are in the bottom left, okay? So they're the ones that are the easiest to remove. Okay, so, and that actually has something to do with the size. If you're a really small atom, you want to hold on to your electrons. If you're big, you might be able to lose a few electron pounds, if you will. But that might be something we're going to talk about in a second. But here's the trend, so you can have this in front of you when you do some of the problems, okay? It's up and to the right. Okay. So the periodic trends in ionization energy are explained by the same influences that explain atomic size trends. So ionization energy decreases down a group because the electron that is removed is further away from the nucleus. And so the attractive forces between the electron and the nucleus decrease the further you go away. And then the nuclear charge, meaning that the outermost electrons, the atoms of the main group elements within a period are in the same principal energy level. If that's the case, the ionization energy generally increases across the period because the electron is removed is attracted by an increased quantity of positive charge as the number of protons increases. Okay, as the attractive force becomes stronger, the energy required to remove the electron will increase. Okay, so again, they're holding on to them more tightly, basically, and it's harder to remove them. Okay, so that's maybe a lot of words. Let's do some examples. So list each of the following groups of elements in order of increasing first ionization energy. So again, you could write them out as they would appear in the periodic table. So actually the first one is already written out. They're all in the same period there. They're all in the same row in this order. So beryllium, then nitrogen, then fluorine. And remember, our trend is up and to the right. Okay, right? Increasing, going up and to the right. So that's our trend. So if it's increasing going to the right, they're all in the same period here. So it's going to be beryllium, then nitrogen, then fluorine. Okay? What about here? Well, these guys are all in the same column. Okay, so you have fluorine, chlorine, and bromine here. So if it increases going up, basically, this is going to be bromine, chlorine, fluorine. Okay, so this is increasing first ionization energy. Okay, so that's our second trend in the periodic table. And I think we'll stop there, and then we'll, in the next video, talk about some more trends and these things called metals, nonmetals, metalloids. We'll kind of put all that information together, okay? So we'll stop with these two trends, which is atomic size and ionization energy. In the next video, we're going to talk a little bit more about trends in the periodic table.